So going back in almost 100 years ago, in 1926, Tesla stated, when a wire is perfectly applied, the whole Earth will convert into a huge brain. This somehow is part of the dream we have with 6G. And if you go back to the basics, it's the only question we're going to have about. We are really trying to understand why we have been always racing for more and more in the communication system from 2G. Actually, if you look what are the basics behind what we are building communication system, so this actually is a very simplified version of the channel capacity. We find what happened in wireless communication system. Actually, what you see that actually what you can gain is you can have capacity by increasing the bandwidth of the communication. That's the reason we go for higher spectrum, like waves, sub-terrestrial communication, or we can have a number of uncorrelated paths to go together. That's the reason we go for example, massive MIMO, self-free communication, and so on. And actually, we can also improve the quality of the signal we see. So that actually, when we speak about all these problems about duplex modulation, with new waveforms, interference cancellation, and so on. So, and all this actually is dictating the thing that we have to go every time for a higher capacity. And actually, what we've been doing 5G, look for this higher capacity, this factor 1000, indeed was actually go for a better use of the spectrum and also to actually explore the spectrum with a band and actually achieve kind of factor 10 in terms of improvement of the capacity. And actually densify the network and also introducing this massive MIMO with a different path. Here again, target factor 10. In truth, here's where we gain the more. Most actually here we got much more than factor 10. Here in the bandwidth we have less than factor 10 in most of the scenarios. And then other new approaches for the signal to noise ratio to the efficiency of the communication in terms of antenna gains, going higher spectrum can have better antenna gains, in terms of noise cancellation, in terms of new waveforms and so on. And actually was approached. And actually that stressed a lot of the system because we need to conceive, there's no freemill hardware that can really work at that kind of frequency. We have to conceive systems that can work with that narrow beams for communication. So there's a lot of management in terms of the algorithms going behind and so on. About this densification of the network, that's good. We did a good job, but actually, the more you densify the network, the more you're prone to interference to neighbors if you want to reuse the spectrum. So actually, we start to really be in a point where actually this is a big challenge to go. And then here as well, we see that since tens of years, we are progressing slowly, because we already did a lot of job with these new coding techniques, waveforms. So, but this actually goes really for an approach which is very classical, in which we receive information as from the end to the top to the two ends, there's just stupid agents. There's no artificial intelligence, there's no machine learning. We just content blindly send data, transfer data from one side to another. And actually, it's like pressing randomly on a keyboard letters, trying to be absolutely precise. So the point is that we are pushing the limit of being ultra precise, while on the contrary, on the other side now, we have intelligent agents who can do something different. So these actually give us the thing that we have been working on, these three major technology pillars: sub-terrestrial communications, the intelligent communication and sensing, the new material intelligence, intelligent antennas in 6G, and we do that through the extensive use of machine learning AI in order to optimize and automate these systems is more and more complex. But again, why should actually still go for this increased capacity, while if we send something that's not just blindly transmitted, but it's understandable, shareable by intelligent agents, can be completely reduced and compressed? And actually, there are three major paradigm shifts that we are exploring in research for 6G. The first one is what we call goal-oriented communication. There was a talk yesterday about intent communication, intent networking. There's a kind of link. Here's more at the physical level. And actually, the idea is that instead of just sending blinded data as they are, you actually select, you filter, and you also tune the precision and the or what you send between transmitter and receiver depending on the goal you have at the receiver. Then, so the second point is actually what's been introduced with this recoverable intelligence surfaces. In general, we say, but I think that instead of having a communication system, which and the channel which is given by nature, now we can reshape and actually remodel the channel in an active way through the use of controllable relays around the network. The third one, or the one I would say I'm more fan of, is what we call AI native semantic communications, where actually we move for this content blind communication to share only what cannot be deduced or inferred by an AI or either by a generative AI. So we just send some elements that enable the understanding, and around this understanding we can do it. So let me show a very small example on that. Manage that. Okay, first of all, this actually changed the way how we approach all these pillars, and we add a new pillar. So actually the semantic oriented communication one. For example, we changed the way we conceive the hardware, and actually also we deal with the imperfection on the hardware. For example, power amplifier, we have a different way to compensate the issues behind. In the intercommunication and sensing, by semantically transmitting, we have a different way to compound, fuse actually the data we receive. And for intelligent surface, also we show actually that we can have a different way to use part of the surface for different users. And then, of course, there's a fundamental research is done on this generative AI and semantic communication. So now, tell me if you can read this text. Some of you maybe know that. This is the key part. This is a text, which is a horrible noise, right? This is a very bad transmission, but you're able to understand. This is because you are a reasoning somehow unit. So the point is that by exploiting the text, that you have intelligence at the transmitter and the receiver, you can relax your communication. You do not need to have an ultra good signal, but at the end you can correct. Then open up a lot of opportunities. We show that we can have different kind of waveforms, we can have different kind of power amplifier, different kind of beamforming algorithms, different kind of resource allocation algorithm, and so on. Because indeed, you ask the system that you can be average good, and I can do the rest. And this actually, from one side, you can compress a lot, because, for example, you do not need to send all this letter, just can random generate some of this letter, but you can also just accept there's noise around. So I like to end this probably start for the panel. I say that this approach with AI is like having a French couple sharing a piece of bread. In France, I can do this example. So the first time they meet up, they introduce each other, they ask kindly probably what they want to do, and they thank each other after receiving. Then after a few months, they know each other. And here, again, it's difference. Every time you connect in the network discover yourself. Every time you go home and you connect to your Wi-Fi, use the telephone and say, hi, it's me, who are you? And you start a connection. Here, the idea is that actually, because we have AI, we profile, actually, we associate users. So you know each other, you ask for a very brief description, and you have a brief thanks. Then, after years, there's no introduction anymore. You expect each other to do the action, a request, and you have a very short request and there's no thanks. And after a whole life, you're just able to hear each other and you just wait for the next time. So this is something where we go from the content blind, the path to, unfortunately, there's a block here, from content blind to this semantic communication approach, in which by knowing each other, by somehow aligning the way you reason, you can say less and less and less. And it's something that we have not been exploiting much, almost not at all, in up to 5G, but this is the key by using intelligence. So if you want to have more information about, there's a number of also information you can read. There's a very nice Nature paper I wrote about that, and another point anyway, you can contact me. But again, introducing AI is not just to optimize the network, but also to change the way you define information to be shared.
Yeah, if you're able to take a question or two, that would be great. I know you have to travel.
Any questions?
Hi. So in the context of using semantic communications, at what level or what layer of the stack do you expect that to occur? Is that actually in the content? So I'm describing a cartoon of a cat chasing a mouse around a kitchen, or is it much more in terms of the network protocol layer or somewhere in between?
Thanks for the question. Actually, it will be on multiple levels. What actually I would start to say that to introduce semantic communication, either to use any kind of AA native communication, you need to change architecture. This is under discussion to have AI plane. We call actually, our words, we call the semantic plane. So where you convey all this control, all this feedback information. So for example, if you have an error, you need to understand if it's just a voice noise, or if there's a lack of understanding of the receiver, or the lack of a good extraction of the semantic of the transmitter. So you need this plane. So this is something that anyway will be piggyback on this AI plane that's under discussion in different standards. So then, given that, you can operate that at the physical level. You can really change the way you do your waveform, for example. But you can also work at the MAC level on the resource allocation. You change the way you allocate resources. For example, easily you understand if a user they're semantic, either not semantic, they coexist at the same time, you have a kind of scheduling if you only have a homogeneous system with only semantic users in one way and so on. So you work at the semantic level, and then at the application level, that's something that actually we are just starting to explore, where there is an entry problem we are about to solve. Actually, also there's a team in Orange working a lot on that. Is actually that the way we represent the data change the type of application that can access somehow to the network itself. So at the physical MAC layer, we make some option about how to represent the data, and that precision, the ways represent actually might be compatible or not with some kind of application. So we are operating multiple level.
Thanks, Dean, and thanks, Emilio. If you have time for one more question, I'm just interested to understand what kind of a load this would put on either the sending or the receiving device in terms of being able to translate the basic data into a semantic.
Okay, so first of all, in terms of energy consumption, we're running this experiment at the moment, so I cannot tell the number. I can tell first of all that when you apply the semantic approach, our experimentation, but not only us, because actually now it's a worldwide community doing that, that we can compress between a factor of 500 and a few thousand, depending on the specific data you're dealing with, depending on the specific maturity of understanding between transmitter and receiver, first of all. So anyway, first of all, it means you have to transmit, for example, 1,000 less, okay? Now, of course, there's a cost in terms of extraction of the semantic and actually interpretation of the semantic of the receiver. It's actually not that complex, because depending on how much you compress, okay? And depending how much the transmitter receiver have been transmitting between us, then actually we can use multi-head attention mechanism. I would say off-the-shelf basic AI components will actually do not require much processing. So in terms of latency, we explore that, and we saw that we are faster with the semantic communication. So within the compression, so we send less, and then we have to this processing more. In terms of energy, something undergoing, but the first time approach is that we have good benefit anyway.